let us take another interesting problem. So number 5. Consider the series sigma n upon 2 raised to n. That is, it is also written as 1 upon 2 for n equal to 1. Then 2 upon 2 square plus 3 upon 2 cube plus 4 upon 2 raised to 4 and so on. To discuss the convergence of this, we need to find the nth term. Here sigma an is sigma n upon 2 raised to n. So that means an is equal to n upon 2 raised to n. Okay, this is a tricky problem. So first what I will do in this, to find the sum a1 plus a2 plus a3 and so on up to an, I will consider the next two terms as an plus 1 and an plus 2. So therefore an plus 1, putting n equal to n plus 1 here, we get n plus 1 by 2 raised to n plus 1. And an plus 2 is n plus 2 upon 2 raised to n. Okay. Now, if you observe that the difference of these two, an plus 1 and an plus 2, that we can write as n plus 1 by 2 raised to n plus 1 minus n plus 2 by 2 raised to n. This I can write as, this is n plus 2 over here. Yes, forgot here, n plus 2. You have to put n is equal to n plus 2 to write down the n plus 2 term. And taking the LCM here, 2 raised to n plus 2, what we get here is 2 times n plus 1 minus n plus 2. 2 times n plus 1 minus n plus 2. So this gives us that 2 will be cancelled. Okay. So what will be left is 2n minus n. So it is n upon 2 raised to n plus 2. This will be left. So that the difference of this an plus 1 and n plus 2, we have proved that it is equal to n upon n plus 2. So this I can write as an plus 1 minus an plus 2 is equal to n upon say 2 square into 2 raised to n, which is nothing but 1 upon 4 times n upon 2 raised to n. And n upon 2 raised to n is our nth term. So I will write 1 upon 4 into an. Okay. So from this I get a nice expression for the nth term in terms of the other terms of the sequence. So this implies I can write an is equal to 4 times an plus 1 minus an plus 2 for every n is equal to 1, 2, 3 and so on. And we want to find the sum Sn, which is given by a1 plus a2 plus a3 up to n. So putting n equal to 1, 2, 3 up to n, we can write a1, the first term, as 4 times a2 minus a3. a2 is equal to 4 times a3 minus a4 and so on. The last term will be an is equal to 4 times an plus 1 minus an plus 2. And if we add all these terms, all these n terms, what you get adding all this is, observe on the right hand side, this a3 will be cancelled. Okay, and a4 will be cancelled. So likewise this and this term will be cancelled. So adding all this, we get Sn, because the left hand side is a1 plus a2 plus a3 up to an, and this will get as 4 times a2 minus an plus 2. Only this term and this term will be left. So that is nothing but 4 times a2. a2 means the second term. Putting n equal to 2 in this, in the original sequence formula, that is n equal to 2 gives you 2 upon 2 square. So it is 2 upon 2 square, 2 upon 2 square, and minus n plus 2, which is nothing but n plus 2 upon 2 raised to n plus 2. Now taking the limit of this as n tends to infinity, limit n tends to infinity of Sn is equal to limit n tends to infinity of this 4 times 4 minus n plus, sorry, this is not 4, it is 1 upon 2 minus n plus 2 upon 2 raised to n plus 2. So this will be left, correct? And limit of this is 0, because we have formula that if you have this kind of expression or a sequence, limit n tends to infinity, say n upon a raised to n is always 0 if a is greater than 1. So I'm using this formula. You can call this as n plus 2 as k. So it is k upon 2 raised to k type expression, and as n tends to infinity, k also tends to infinity. So this limit is 0. So this is equal to limit n tends to infinity 4 into 1 by 2 minus 0. So that is nothing but 2. So this limit Sn exists and it is equal to 2, and that means the given series is convergent. That is sigma n upon 2 raised to n is convergent, and not only that, its sum sigma n is equal to 1 to infinity n upon 2 raised to n is equal to 2 is proved. Okay, so this is a very nice example, and we can also find the sum of this series in a different way, but for that we have to assume the convergence of this series. Suppose the series as sigma n upon 2 raised to n is convergent is known, and if you are asked to find only the sum, then in some competitive exam you can use this technique of finding the sum directly. So let me show you that interesting technique. Okay. So another method. What I will do is, suppose the sum, the required sum is say S. Suppose S equal to sigma n equal to 1 to infinity n upon 2 raised to n. So that is S is equal to 1 upon 2 plus 1 upon 2 square, 2 upon 2 square, 3 upon 2 cube plus 4 upon 2 raised to 4, and so on. So it is this series, and suppose the sum of all these terms is equal to S. What I want to do here is let us divide it by 2, both the sides. So like this way, dividing both the sides by 2, what I will get is S by 2 is equal to, say, 1 by 2 square, okay, plus 2 by 2 cube plus 3 by 2 raised to 4 plus 4 by 2 raised to 5, and so on. So that one power of these two will be increased. Okay, and now, so taking the difference, we get S minus S by 2 in the left hand side. On the right hand side, I will keep this 1 by 2 as it is, and then this 2 by 2 square minus 1 by 2 square, that is 1 by 2 square, then 3 by 2 cube minus 2 by 2 cube, that is again 1 by 2 cube, then 4 by 2 raised to 4 minus 3 by 2 raised to 4 is 1 by 2 raised to 4, and so on. Okay. So this you can see that we'll get s by 2, and this is a geometric series, infinite geometric series with the common ratio 1 by 2, and first term is also 1 by 2. And for infinite geometric series with the common ratio r and first term is a, we know that its sum is given by a upon y minus r if mod of r is less than 1. If the common ratio r lies between minus 1 and 1, then we can write down the sum of this infinite series, geometric series, as a upon 1 minus r. So this infinite geometric series, the first term is 1 by 2 here. The first term is 1 by 2. So a upon 1 minus r means a is 1 by 2 upon 1 minus the ratio, that is 1 minus 1 by 2. So what you will get is s by 2 is equal to 1, because 1 by 2 upon 1 by 2 is 1, and that gives you s is equal to 1. Sorry, s is equal to 2. So s is nothing but the sum of the series sigma n upon 2 raised to n. So this is another interesting method of finding the sum directly for an infinite series of this type. Okay, n is equal to 1 to infinity. Let's take another example of the same type. It is a little bit more difficult to prove it, the convergence using the definition. So the next problem. The next problem is number 6. Discuss the convergence of the series, say sigma n upon 3 raised to n is equal to 1 to infinity, which you can also write as 1 upon 3 plus 2 upon 3 square plus 3 upon 3 cube, and so on. Okay. So first of all, note that the series sigma an here is sigma n upon 3 raised to n upon 3 raised to n. So therefore, an, the nth term, is n upon 3 raised to n. Again, I will use a similar technique and write down the next two terms of this series. So this implies n plus 1 is n plus 1 upon 3 raised to n plus 1, and n plus 2 is equal to n plus 2 upon 3 raised to n plus 2. Okay, so taking the difference here of n plus 1 and n plus 2, what I get is n plus 1 by 3 raised to n plus 1 minus n plus 2 by 3 raised to n plus 2. This is equal to, the LCM will be 3 raised to n plus 1, 3 raised to n plus 2, the highest power. And when you simplify, we have to multiply this by 3. So 3 times n plus 1 and minus, this is multiplied by 1. So minus 1 into n plus 2. So simplifying this, we'll get 3n minus n, that is 2n, and 3 minus 2, that is plus 1 upon 3 raised to n plus 2. So what I have proved here is n plus 1 minus n plus 2 is this thing. So further writing in a different way, n plus 1 minus n plus 2 is equal to, this I would like to separate in this way. So 2n upon 3 raised to n plus 2 plus 1 upon 3 raised to n plus 2. And this we can write as, say, 2 upon, I will take 3 square separate, so 2 upon 3 square into n upon 3 raised to n, and plus 1 upon 3 raised to n plus 2 as it is. And you know that what is this term, n upon 3 raised to n? It is nothing but the given sequence an. So I can now rewrite this thing as an plus 1 minus an plus 2 is equal to, say, 2 by 9 into an, 2 by 9 into an plus 1 upon 3 raised to n plus 2. What I would like to find is Sn, and Sn means a1 plus a2 plus a3 up to an. So for that I need an, and what I have done here is I have expressed the term an in terms of other terms of the sequence. So from this, if you simplify it, keeping this 2 by 9 times an on one side, we can write this implies 2 by 9 an is equal to an plus 1 minus an plus 2 minus 1 upon 3 raised to n plus 2. And that implies an is 9 by 2 times an plus 1 minus an plus 2 minus 1 upon 3 raised to n plus 2 for n is equal to 1, 2, 3 and so on. Now we'll find all the terms of the sequence a1, a2, a3 up to an and then add them to get the value of Sn. So therefore, we get the first term a1 is equal to 9 by 2 into a2 minus a3, okay, minus 1 upon 3 cube, correct? By putting n equal to 1, 1 plus 2 is 3. Second term, a2 is 9 by 2 into, putting n equal to 2 here, 2 plus 1 is 3. So a3 minus a4, putting n equal to 2 here, minus 1 upon 3 raised to 4. Now, using this symmetric or this pattern, we can write the next term directly, that is a4 minus a5 minus 1 upon 3 raised to 5 and so on. And the last term, that is nth term, is this only, which I am writing here, so that we can understand what will be left when we add all this. So an is 9 by 2 times an plus 1 minus an plus 2 minus 1 upon 3 raised to n plus 2. And we want to add all these terms. Okay, adding all these terms, what we get in the left hand side, a1 plus a2 plus a3 up to an, and that is nothing but Sn. So this implies Sn is equal to, here, if we add all these terms, so a3 gets cancelled, then a4 will be cancelled, and a5 will be cancelled. So this term will be cancelled with this term, the previous term, and all this will be added. And 9 by 2 is common in all these sums. So Sn, that is a1 plus a2 plus a3 up to n on the left hand side, is 9 by 2 times, here what is left is this first term a2 and minus an plus 2. So a2 minus an plus 2, this is I am writing separate, and for the remaining numbers, this 1 by 3 cube, what we'll do is taking minus sign common and minus into 1 upon 3 cube minus 1 plus 1 upon 3 raised to 4 plus 1 upon 3 raised to 5 up to 1 upon 3 raised to n plus 2. Okay. So this we can write as, by putting the values of an and n plus 2 in this, 9 by 2 times, what is a2? Our sequence, just recall, our sequence an is n upon 3 raised to n. So putting n equal to 2 here, what I will get is 2 upon 3 square, right? Minus n plus 2, putting n equal to n plus 2 is n plus 2 upon 3 raised to n plus 2. And this, from this bracket, I can take 1 upon 3 cube as a common factor. What I will get here is 1 plus 1 upon 3 plus 1 upon, say, 3 square, and finally 1 upon 3 raised to n minus 1, because n minus 1 plus 3 is n plus 2. So we will be getting this. Now it is easy to write down the next step immediately. This implies we'll get Sn is equal to 9 by 2 into, this is 2 by 9 minus n plus 2 by 3 raised to n plus 2 minus 1 upon 3 cube. And now this thing is the sum of the first n terms of geometric sequence. So we have a formula for that. You have studied in schools. So this I can write as a into 1 minus r. A is the first term. We know that a plus ar square up to ar raised to n minus 1 is given by a into 1 minus r raised to n upon 1 minus r. So to find the sum of the first n terms of a geometric sequence, we use this formula, which we have already discussed. So first term is a, that is 1. This is the first term. So a into 1 minus r. R is 1 by 3. Common ratio is 1 by 3. 1 minus 3 raised to n upon 1 minus 1 by 3, using that formula. Okay. So simplifying this, what we get is Sn is equal to 9 by 2 into 2 by 9 is 1 minus this is 9 by 2, and this I am writing as it is, n plus 2 upon 3 raised to n plus 2 minus 1 upon 3 cube into this 9 by 2 is also there. So let me write here minus 9 by 2 into, this will be multiplied with this term, into this thing. This is 1 minus 1 upon 3 raised to n upon 1 minus 1 upon 3, that is 3 minus 1, that is 2 by 3. Okay, we will get this thing. Now, taking the limit here as n tends to infinity, because we want to find the limit of Sn. So what I will get here is, just a minute. So taking limit as n tends to infinity here, we get limit n tends to infinity Sn is equal to limit of this. So limit n tends to infinity of 1 minus 9 by 2 into n plus 2 by 3 raised to n plus 2. Okay, and minus, what will be left here? This is 3 cube and this is 9. So we'll get 1 upon 3. So it is 1 upon 2 into 3, that is 6. And this we are writing as 1 minus 1 upon 3 raised to n upon 2 by 3. We can write as 3 by 2. So let me write 3 by 2 here. This into 3 by 2. Okay. So again, this 3 will be cancelled. So this limit, now we can write directly as 1 minus 9 by 2, 1 minus 9 by 2 into 0. Because as n tends to infinity, n plus 2 upon 3 raised to n plus 2 is 0. Minus, it is 1 by 4. And limit of this is 0 again, because r is less than 1. So we are using two formulas here. Let me just write here, because I am using two formulas. One is limit n tends to infinity, n upon a raised to n is equal to 0 if a is greater than 1. So that I am using here for this. This is of the form n upon a raised to n, and a is equal to 3, which is greater than 1. And for this, we are using the known formula of limit n tends to infinity r raised to n is equal to 0, provided mod r is less than 1. Okay. And here r is equal to 1 by 3. So this limit is also 0. So what we are left with is 1 minus 1 by 4. 1 minus 1 by 4. So it is 3 by 4. Okay. So this limit exists, and therefore the given series is convergent. So thus sigma n upon 3 raised to n is convergent, and the limit, I mean the sum, sigma n upon 3 raised to n is equal to 1 to infinity, is 3 by 4. Okay. So this we have done using definition of convergent series. Now Sometimes if you are asked to just find the sum of this series without discussing the convergent, or if you can check the convergence of this series using some other techniques, then there is another alternative interesting method. I am just discussing that. It is similar to the previous problem, and that is also useful in some cases. So suppose we take the sum S equal to sigma n upon 3 raised to n is equal to 1 to infinity. Okay. So that is S is equal to 1 upon 3 plus 2 upon 3 square plus 3 upon 3 cube plus 4 upon 3 raised to 4 and so on. Okay. Let us divide this by 3 on both the sides. So what I will get here is dividing by 3, S by 3 is equal to 1 upon 9 plus 2 upon say 3 cube, or let me write here this as 3 square, 1 upon 3 square plus 2 upon 3 cube plus 3 upon 3 raised to 4 plus 4 upon 3 raised to 5 and so on. Okay. Again, we want to say add these two terms, and what I will do is I will just take the difference of these two in this order. So I will take the first term separate in this S and then subtract these terms in this manner. This minus this, this minus this, this minus this. So what I will get, subtracting these two equations, S minus S by 3 on the left hand side. On the right hand side, 1 by 3 is fixed, plus for the other terms, this is 2 by 3 square minus 1 by 3 square, that is 1 by 3 square plus 3 by 3 cube minus 2 by 3 cube is 1 by 3 cube. Then 4 by 3 raised to 4 minus 3 by 3 raised to 4 is 1 by 3 raised to 4 and so on. So you can immediately understand what is the next step. This is 3s minus 3, s minus s by 3 is 3s minus s. So it is 2s by 3. Okay. And this is an infinite geometric series with first term is 1 by 3. The first term is 1 by 3 and the common ratio r is also 1 by 3, and it is satisfying the condition mod of r is less than 1. So therefore this series is convergent and its sum is given by this formula. As we know, it is a upon 1 minus r. So I will write a, that is 1 by 3 upon 1 minus r. So that is also 1 by 3. So a is 1 by 3 and the ratio r is also 1 by 3. And let us simplify this. So what I will be getting here is 2 by 3 times s is equal to, this is 1 upon 3 and this is 2 upon 3. Okay. So taking this 3 will be cancelled and we will get 1 by 2, and that means s is equal to 3 by 4. We have found the sum in a different way. Sigma n upon 3 raised to n is equal to 3 by 4 for n equal to 1 to infinity. So in this lecture, we have discussed how to check convergence and divergence of infinite series using only definition, and seen some interesting techniques also. In the next lecture, we'll be starting some theorems on convergence and divergence of series. Remember that there are many other tests using which we can discuss the convergence of this series also. But just to understand how to apply the definition of convergence series, we have taken these examples. So thank you.